Hello, my name is Yilu. I'm an undergraduate student in Southeast University in China. The paper I will be presenting today is titled Prediction-Based Early Warning System for Overload of People in Metro Stations. Firstly, why are we working on such a system? This is because our urbanization is increasing and the resulting urban traffic problems are becoming more and more obvious. There's no doubt that the crowded traffic at the station is a very dangerous phenomenon. If the station management can intervene in the station before people is too crowded and evacuate them in time, this is undoubtedly a good situation. For this purpose, we have designed a prediction-based early warning system. So how is this system built? We divide the system into four parts. The first step is model training and prediction. We record the passenger number into the historical data and use it to train the model. At the same time, in addition to that, we also get the real-time data and use the trained model to predict the passenger flow after the real-time data and get the data of test sets. Well, before we perfect the system, let's first use the test set data to further improve the system rather than using the forecast data to predict the traffic. The second part is threshold determination, which is not much related to the previous step of machine learning, but the station managers still need to use the historical data used in the previous step because they need to determine whether the station is becoming overcrowded based on their own experience. And if so, they have to record the overload of people in the database and determine what threshold is to judge the overcrowding of station. All right, let's get back to machine learning. After we use the model to predict the flow of people, we find that the predicted one is not completely consistent with the actual one, but there are inevitably some deviations. In some cases, these deviations are often very serious, so we need to correct the result. First, we select the confidence level of model, and after that, we introduce the correct factor alpha to correct our results. In this way, our prediction system is completed. Now let's look at the second branch under the model from step one. We can use this model to predict the number of people. After we have finished that, we need to use the alpha to correct our prediction because the predicted value is often lower than the true one. In the final step, we compare the revised predicted value with the threshold we obtained from the station managers in step two. If the predicted value exceeds the threshold, then the station staff will need to intervene. Otherwise, we do not need to worry about that the station will be overloaded at the next moment. In the machine learning part, we use the long short-term memory model. This model is like a human cell. It can remember recent events clearly, and it can forget earlier events. Forgetting things that happened too early is a good thing because it can keep the model from clouding its judgment of the present. We used five metrics to determine how well the machine learning feed works. Square error, mean absolute percentage error, R square, and adjusted R square. We made predictions of 7 months of data for 46 stations, and we used the first 85% of the data as the training set and the last 15% as the test set. We selected one of them as a case study. The blue line in the graph is the actual value, which is how many people in this station actually has, while the green one is predicted value, which is how many people our model predicts. If we look at the figure carefully, we will find that the actual number of people flow is always a little higher than that of the predicted value in peak period of people flow every day. In fact, we find the same problem in the forecast for the remaining 63 stations. This is a serious deviation in our risk assessment, so we need to find some value to correct our prediction. We introduce a preliminary alpha, and in the test set, we can find alpha for the number of people in a certain period of time. Um, since the correction coefficient is to reduce the forecast deviation of the model when the passenger flow is high, we'll only consider the case where the predicted value is greater than 10 when defining the correction coefficient. But on rare occasions, our actual value will be less than the predicted value. Fortunately, in this case, we can still use this formula to get a revised forecast. Again, we take station 102 as an example. In the test set, which accounts for 15% of the total data set, we further select the time period when the actual number of passengers is 10 or more. After obtaining alpha for them, we then sort every alpha to get the result as shown in the screen. We can see that in the case of very low accuracy, especially below 10%, our data hardly need to correct it as the accuracy increases and the value of alpha become larger and larger. Taking 19% accuracy as an example, if the predicted number of people at the station in the next moment is 100, the revised prediction number is 136. Note, however, the higher accuracy is not always better. As with 99% accuracy, the revised prediction is about twice as many as the original prediction. In that case, the station's management system might keep alerting all the time, but nothing is actually happening. That is all for my report. Thank you very much.